All right, so if you're a security architect, you know the drill. For decades, trust has been a simple, binary switch. You're either trusted or you're not. Well, today we're diving into an architecture called PTC-Ω that basically throws that entire idea out the window. We're going from a world of declared trust to a world of computed trust.
So here's how we're going to break it down. First, we'll talk about why that old binary model is broken. Then we'll get into the real guts of the system, the multi-validator quorum, and this really cool concept called the dynamic trust envelope. After that, we'll see how all this math gets burned into actual silicon, look at some wild real-world uses, and then wrap up by asking, so what's next?
Okay, let's get right to it. Traditional security is all about that yes or no answer. It's black and white. PTC-Ω comes along and says, nope, the world is way too complex for that. It suggests that trust shouldn't be a light switch. It should be a dimmer dial, a continuous value, a scalar that goes up and down based on what's happening right now.
And this quote right here, this is the whole philosophy in a nutshell. We're done just taking a system's word for it when it says, hey, I'm trustworthy. Instead, this architecture forces it to prove it with verifiable math. It's a fundamental shift from a static label to a dynamic, constantly updated reality.
So what is this thing officially? Well, here's the formal definition. And for all you architects watching, two words should just leap off the screen: external and coprocessor. This is absolutely key. This isn't just some software running on the host it's supposed to be protecting. No way. This is an independent, mathematically driven referee that sits on the outside, watching, validating, and if it has to, blowing the whistle.
But hang on a second. If you have an all-powerful external referee, you have to ask the classic question, who watches the watchers? What's to stop that referee from becoming a single point of failure itself? Well, that's where the first core mechanic comes in, the multi-validator quorum. The whole architecture is designed to prevent this one specific nightmare scenario they call single validator fossilization, and it's as bad as it sounds. It's what happens when one lone validator, maybe it's been hacked, maybe its software is just ancient, gets to unilaterally decide what's true and what isn't. It can essentially hold the entire network hostage. And here's how it stops that from ever happening. Any emission from the system has to run this brutal three-part gauntlet. First, it has to pass through something called the SE44 semantic gate, which is basically a bouncer checking the quality of the data. If it gets through, it then needs signatures from at least two independent validators. And even then, the combined reliability score of those validators has to be above 0.75. It's a triple lock door.
So let's just focus on this number, 2. This is the cornerstone of the whole defense. By demanding that at least two validators agree, the architecture makes it mathematically impossible for a single, compromised agent to hijack the system. Consensus isn't a suggestion, it's a requirement. All right, next up is one of the most elegant parts of this whole design, the dynamic trust envelope. This is where the system gets really clever and introduces the concept of time, making sure that trust is never a permanent asset.
Okay, here's the full formula, and I know it might look a little intense, but don't worry about all the symbols. I just want you to focus on that very last part, that e raised to the power of negative lambda delta t. That's a classic exponential decay function. All it means is that the value of any trust score automatically and naturally fades away over time. And the security implications of this are just massive. It means an attacker can't land one lucky shot and own the system forever. The impact of their attack will literally just evaporate. It forces every agent to constantly re-earn its trust. A single bad actor can't just seize control and hang on. Its dominance will decay to nothing without constant backup from the rest of the quorum. Okay, so we've covered the theory and the math. But for any architect, the question that always comes next is, that's great, but how do you actually build it? So let's look at how these abstract ideas get translated from a formula into real physical hardware. What you're looking at here is the high-level schematic, the data path designed to be implemented on an FPGA. You can see the flow. A signal comes in from the host system, it's parsed, its drift is calculated, and then it has to face that C44 gate. Only if it passes does it get recorded. This is the physical assembly line that enforces all the rules we just talked about. Now let's zoom in on this specific block, the reliability engine. Remember that reliability score R sub I that needed agreement? Well, this shows us exactly where it's calculated. See that label, DSP unit? That's a digital signal processing unit. This is a very deliberate choice, using a piece of hardware that's purpose-built and hyper-efficient for exactly this kind of math.
And this table just makes it perfectly clear. These abstract concepts aren't just vague ideas. They have a direct one-to-one mapping to efficient hardware primitives. The omega operator becomes a DSP function. Exponential decay becomes a lookup table. The reliability score becomes a parallel adder. This is determinism, enforced in silicon.
And let's revisit that SC44 gate, because it is the final, non-negotiable checkpoint. For any emission to pass, it has to meet these three uncompromising, hard-coded thresholds. We're talking near-perfect coherence, practically zero entropy or randomness, and almost no drift. These aren't suggestions. They're absolute physical limits. Fail just one, and you're rejected, period. So now that we're clear on the internal mechanics, let's zoom back out and look at where you could actually deploy an architecture like this. And frankly, its versatility is one of its most powerful features.
This slide just illustrates that versatility perfectly. On the left, you've got an AI output validator. It uses PTC-Ω to basically fact-check a large language model and stop it from making things up. On the right, a totally different world, a robotics trust layer. It uses the exact same principles to validate a command before a physical robot arm actually moves. It's securing both data integrity and physical safety with the same core logic.
So, as we wrap up this analysis, let's just boil it all down to the core principles. What should an architect really take away from this design?
It really comes down to these four ideas. First, trust is computed, not declared. Stop asking, start calculating. Second, drift is going to happen, so the goal is to bound it, not pretend you can eliminate it. Third, amplification requires identity. You can't trust a loud signal if you don't know who's sending it. And finally, persistence requires reinforcement. Without constant validation from the group, anyone's influence simply fades away.
And that brings us to the final thought. This system is more than just a clever design. It's a new way of thinking. So I'll leave you with this question to chew on. If trust is no longer a matter of opinion, but a verifiable real-time calculation, what does that allow us to build that was impossible before?